Hi, everyone. It's 12 o'clock. Let's get started. Hi, this is Jason Key at SP Grid at Harvard Medical School. Thanks for joining us today. So today we have Thomas White joining us from the Center for Free Electron Laser Science at DESY in Hamburg. So Thomas did his PhD in Cambridge and then has since gone on to do a number of things with free electron laser diffraction. So today, so this is something that's sort of near and dear to my heart, the time-resolved X-ray diffraction from protein structures. So today he's going to tell us about processing serial crystallography for using CrystFEL. So Thomas, are you there?
Yep.
All right, yeah, go ahead.
Okay, thanks a lot. So yeah, thanks for the intro. Welcome to this webinar on CrystFEL. First slide is the systems check, so assume everything is ready to go.
Looks good. Go ahead.
Yeah, good. Okay, so before anything else, I'd just like to thank the contributors to CrystFEL. Development is led by me at the Center for Free Electron Laser Science. There are code contributions from many people, both inside CFEL and outside. There's also been testing and feedback from many people, so especially the people who've contributed code, but also some other people have been particularly helpful there, and words of wisdom from many people, in particular those people at the bottom there. So what is CrystFEL? So it's a data processing software suite for crystallographic data acquired in snapshots using a serial methodology. I'll explain what that means in just a second. It's been under development since 2009. Version 0.6.1 will be released very soon. There's just a few more things we'd like to check up on and straighten out first there. It's free and open source software under the GNU GPL version 3. So that means you have access to the source code, and also you can make modifications and distribute your changes if you want to. It has user-oriented development, so that means that we try to pay attention to things like user interface, documentation, stability, and so on. And the website's there, otherwise you can just search for CrystFEL, you'll find it straight away. At the bottom here is the official citation for CrystFEL. So what is serial crystallography all about? So there's been a lot of fuss made recently about free electron lasers. Free electron laser allows you a way to sidestep radiation damage by using very short, intense X-ray pulses. Pulses are so short, in fact, that most of the damage processes don't have time to take effect. The crystal is still destroyed, in fact, after one pulse, but not before we get diffraction. So a popular way of doing crystallography at a free electron laser is like this in this figure here. You have crystals in a liquid suspension here, and they're being injected in a liquid stream into the path of the X-rays. When an X-ray pulse hits a crystal, we see a diffraction pattern on the detector. And we only get one diffraction pattern per crystal because the crystal is destroyed, but as I said, not before we get a diffraction signal. So each crystal is in a random orientation, and each diffraction snapshot that we measure has to be processed individually. So essentially, it's like a separate diffraction experiment. Here at the bottom are some citations. So this figure itself comes from this paper, Boutet et al. That was the first high-resolution demonstration of this technique, which we call serial femtosecond crystallography. The lower reference is Chapman et al., and that's the original description of this method at all. So I'll show you later on where you can get loads of more citations if you want to know more about this and what some of the possibilities are. I should mention also that you don't have to do serial crystallography using a free electron laser. So there are also now actually an increasing number of demonstrations of similar techniques done with a synchrotron light source. So that's possible as well, quite popular. So what do you get in CrystFEL? So you get these tools primarily. Each of these does a different part of serial crystallography data processing. So these are what you'll spend most of your time with as users. CrystFEL is primarily a command line piece of software, but some of these are graphical user interface tools as well. As well as the data processing stuff, there are some simulation tools. So in the middle there, you see pattern sim and partial sim. Those are simulation tools. You can use those to generate test data if you want to test your data processing, or if you want to test some other algorithm, something, you can do that. Of interest to programmers will be libcrystfel. That's a shared library of routines. It's not meant to be a general crystallographic library as such, but something higher level. For example, it contains functions like index this pattern or calculate these partialities. So high-level functions that you might use, for instance, in a facility framework. So if you wanted to run this in an online monitoring facility at a light source, you might use libcrystfel for that. Documentation, of course, is on the website for this. So while we're speaking of documentation, you have a number of sources of help with CrystFEL. There are standard Unix manual pages. So if you need help with the program indeximajig, for example, you just type man indeximajig and you'll get the manual page for that. There are help messages as well. So you can run indeximajig -- help, and it will give you a short summary of the command line options. So that's useful if, for instance, if you just forgot what the option was for some particular thing that you wanted to try. The website has a whole number of things that I'll show you in a moment. There's a mailing list, which is used for announcements of new versions. So if you want to be added to that list, just email me, and my email address is on the website. And user support, of course, if you have problems, you can just email me. So here's the website. So there's a few things I'd just like to point out. Of course, there's the front page with news. So here you can look for announcements and new versions if you're not on the mailing list, or for important changes on the website. There's a download page, of course. So here's the latest version. Below that, you can get development snapshots. So if you want to test some new facility, new function, you can use those. You can also use the source code repository, which is a Git repository as well, if you want to be right up to the minute development. Manual pages are here. These are essentially web versions of the manual pages. So if you click, let's say, pattern sim, it's just a web version of that. So you can use that to look things up really quickly. And there's a tutorial. So this contains just an introduction to all the stages of data processing using CrystFEL. So that's a good thing to work through. There's also the best practice guidelines here. So this has just got some helpful hints. Things once you've used CrystFEL for a little while, some things that will make sense to you then, that will just say, okay, you might want to use this option, or you definitely don't want to use this option, or so on, things like that. So today I'm going to demonstrate CrystFEL using some freely available test data that comes from this CXIDB, or Coherent X-ray Imaging Data Bank. So this is at www.cxidb.org, and here you can get many data sets. So if I click Browse Data here, you see the available data sets. Some of these are crystallographic data, not all of them. Some of them are like X-ray imaging data, which is also probably of interest. The one I'm going to use is this ID 21 here. This is some serial femtosecond crystallography data from serotonin 5-HT2B receptor bound to ergotamine. This was acquired using the CXI instrument at the LINAC Coherent Light Source by Vadim Cherezov and collaborators. So the reference is here if you want to read about that. So you can download and extract the data. So here are the data files at the bottom. If you wanted, you could download everything here and reproduce the result in the paper. That would take a long time. So for this demo, what I've done is just downloaded this one, run 130. So now if I swap over to my command line, I've downloaded and extracted those already. So if I look in the data folder here, here's the contents of that tarball. It actually contains 10 runs. And if I look inside one of these, so let's look inside run 135. What you see is some metadata and auxiliary files. So mostly these are configuration for the earlier processing stages. The real data that we want is actually in these folders, data 1 and data 2. You'll see there are a lot of them. So here's the files. These are the files we're mostly interested in. There's one file per diffraction snapshot, and they're in HDF5 format. So if you don't know what HDF5 is, it's a very common scientific data format. It can contain just about anything. It's hierarchical, it's easy to use. There are bindings for almost every language you can think of. So let's use the CrystFEL program HDFC to look inside one of these. So let's see, the HDFC, which is the CrystFEL image viewer. You can look data / CXIDB, let's go to data 1. Tab, okay, 1, 3. So let's choose a random file. So let's try 6, 5. Okay, so there's a random file. So if I open that, first thing you notice is that the panels of the detector are in the wrong places. So this detector, the detector used at the facility where this was taken, has many small panels, and you can see the edges here, these little squares, these rectangles. You can see it doesn't make sense as a real image. So here we see the panels as they're laid out in the data, which is not the same as the physical layout. So CrystFEL uses a thing called a geometry file to tell it how the contents of the HDF5 file relate to reality. So I have one already, so I'll probably just close this. I've prepared one already in this 5ht2b .geom. So let's look inside that. It's just text. Now it contains information. So for example, here is where to get the detector position in the HDF5 file, where to get the photon energy, so like the wavelength. There's some bad regions, there's some information about how the detector is assembled physically, and then there's the coordinates of all these panels and the transformation matrices that are needed for them. So this goes on, there's 64 panels in this case. So I simply run HDFC again, but now I'm going to give it that geometry file. So 5ht2b. So I've simply added the command line parameter -g and then that geometry file. So if I run that, we should now see that the panels come up in their physical locations. So that's much better. So there's quite a number of things you can do with this view. So let's look in the view menu. You can change the color scale. So for example, let's have an inverse monochrome, black and white color scale. There's the boost intensity thing, is probably one of the most important ones. Note the keyboard shortcut F5 for this. This just compresses the color scale by the factor that I give. So at the moment it's on 1. So let's set it to 5 and we can see a bit more detail. Let's go a bit higher, so I'm just going to press F5. Let's try 10. We can see the peaks in the diffraction. So so there's a data set. So we had one diffraction snapshot. Now we have a whole lot of these that we're going to process. So the first step is to make a list of them. Now the way to do that, or one way to do that, is to just use the standard Unix find command. So it just works like this: to find data dash name goes lcls star.h5 and then redirect that to files.list. So note the filtering here. So I want all of the HDF5 files, or .h5 files, which begin with LCLS. So there are some .h5 files in those folders that are not actually these main data files that we're interested in. So that's the reason why that snippet there is needed. Otherwise, it's just all of the HDF5 files in that folder. So those are now in a big list. So let's take a look at that files.list that we just created. It's simply a text list of all the files. There you go, it goes on and on and on. And if we look at the length of that, just with the word count utility, there's 5,775 images that we're going to process today. Just in passing, lots of small files like this is generally a bad thing. So it's bad for like file systems and the low-level data handling. With CrystFEL, you have the option of using a smaller number of much bigger HDF5 files. So say instead of containing one diffraction snapshot, each file could contain 100 images. You can do that just by modifying the way the geometry file works. And you can read about that in the manual page if you want to. So we're going to take this list and we're going to give it to CrystFEL's core indexing and integration program, which is indexmajig. So I simply type indexmajig, use tab completion there, and -i for input, and then files.list. So hit enter, and it complains that it needs more. So this is a general design principle in CrystFEL, that the programs will moan at you until you give them everything you need. So it's saying it couldn't read the detector geometry from null. Okay, that makes sense. So let's give it the the geometry file, 5ht2b, again, it's just -g, and then the geometry. Try that again. And now it says failed to open stream. So that's referring to the output stream file name, which I'll show you more about later. So let's give it an output. Let's call it tutorial.stream. Enter. And now it's running. So we should see some updates coming in a second. There we go, telling how many patterns it's processed since the last message. Note these warnings at the beginning here. So you should always read these warnings and see what they're complaining about. There might not be a problem, but you should know what's happening. So it says we didn't specify a peak detection method, so it's using the default method there as IF for you. It says you didn't specify an indexing method, so it won't index anything. So that's not what we wanted. Rerun with indexing equals methods. We didn't specify int radius, use the default values, which is probably not appropriate. Now in this case, this is what we want because we don't want it to index anything, so we're not worried about radio or anything. We just want to see how the peaks look. So I'm going to leave that running and switch to another tab. And we're going to examine the results from that as it goes along. Now there are helper scripts in the CrystFEL download folder for this purpose. So this is the folder that you got when you downloaded and unpacked the CrystFEL software itself. So even if it's pre-installed at whatever site you're working at, it's a good idea to download it yourself anyway, so you can get those scripts. You can also find them on the website if you don't want to do that. So in my case, that's in the home directory /CrystFEL. So have a look in there. So here's the source code essentially. There's the source code for CrystFEL. The folder we're interested in is CrystFEL/scripts. So here are the useful scripts, and there's a scripts here to do various different useful things. So probably when you come up against some odd thing you need to do, have a look in here and see if there's someone who's written a script already that can help you. The one we want right now is called check peak detection. So here it is at the top. I'm going to copy that to my working folder. So just copy CrystFEL scripts check peak detection folder. Let's take a look at that inside that script. So again, it's just a text script, it's actually a Perl script in this case. There's a reason that these scripts are kept separate like this rather than being just programs that are installed and that you can just run. And that's that you're supposed to edit them. So for example, if you look here, there are some default parameters for HDFC. And maybe these aren't what you want, so you can change these here, and then you will only have to change them once. And then this version can then apply just to your working copy. For the time being, we don't want to change anything. So let's try running that check peak detection. I simply give it the stream tutorial.stream. I'm also going to give it the geometry file, otherwise the view won't make any sense. So what this script does is it opens HDFC for each pattern in turn. So here's the first pattern in the stream, in the output. And it's shown with the geometry because we gave it the geometry. And also with yellow circles surrounding the peak locations that were found. So again, maybe we want to change the color scale a bit. Let's increase that. And we can now judge whether the peak detection is okay or not. So it looks okay. It's found some strong, maybe there's quite a few weaker ones, for example, here and here, and here that it hasn't found. So it's okay. It's just not great. If I close this, the script will then open the viewer for the next image in the stream. So there it is. So you can look at maybe the first 10 or so of these and decide whether it's working or not, whether you need to make any amendments. Actually, considering we're using the absolute default parameters here, so I didn't set any peak detection parameters at all. This is actually looking reasonably, it's a lot better than I expected. So I'm surprised it works that well, actually. So to stop this peak detection, you simply, because it will go on and on opening the next image until you stop it. Stop it, just go to the terminal and just Control-C. So that's now stopped. So, okay, processing is still going on in the background here. So I'm going to stop that as well. So these HDF5 files that we're processing here actually contain peak locations as well. That's because the prior processing steps for these patterns needed those peak locations, in this case to find the crystal hits amongst a much larger number of non-hits where the X-ray pulse just happened not to hit any crystal. So it turns out that detecting those Bragg peaks is a good way of sorting the hits from the non-hits. And then later on, well, why not reuse those peaks, those peak locations for the indexing integration steps? So using those peaks is really easy. You just have the same command as before. I just add -- peaks equals HDF5. So now it's using those peaks. So just wait for it to get started there. And if we repeated the check peak detection step, we would now see the peaks that is taken from the files instead of the ones detected by that internal algorithm that it was using before. So let's give that a try. Let's just go back to my other tab here and run check peak detection, same stream, same geometry, same everything, and see how it looks now. So you see it looks a lot better. It's picked out, yeah, a much higher number of peaks. In fact, now it's possible that there are some misfound peaks here. So these all look real, but these ones at the edges here, these could just be noise coming above a threshold. Let's close that. Look at the next one. Again, similar story. So maybe some outliers here, but main peak detection is looking good. So we want to actually index and integrate these patterns rather than just playing with the peaks. So stop that from running. So remember this warning here said you didn't specify an indexing method, so I won't try to index anything. This isn't what you wanted. Rerun with indexing equals methods. So there's a choice of indexing methods just as there's a choice of peak search methods. So the one I'm going to use now is MOSFilm. So I type indexing equals MOSFilm. I'm also going to add a -j2, which I'll tell you about in a second. So what this means is that MOSFilm will be used to determine the orientation of each crystal. So MOSFilm is an external program that IndexMajig will call out to and get it to do the dirty work of finding the crystal orientation. It makes sense to do that because MOSFilms have decades of development and tuning of parameters to make the orientation determination work really, really well. So it doesn't really make sense to try and duplicate that too much. And there are some internal algorithms. There's one internal algorithm that you can use in IndexMajig. If you don't, for instance, if you don't have MOSFilm installed, you can also use Diracs and XDS. And in fact, you can use a combination as well to get a higher indexing rate. The indexing program will only be used for the indexing steps, so the orientation determination step. The later stages, which are refinement, spot prediction, integration, and so on, those will all be done by CrystFEL. About the -j2, that's telling it to run 2 analyses in parallel. So if you have a fast multi-core machine, you can use higher numbers here. So I'm just running this on a puny virtual machine, so I'm just using two processors there in parallel. If you had a bigger machine, for example, we have like a 32-core machine, you might use -j32, and it will go a lot faster. So that's running, and it's reporting its progress on the terminal. Now, because we told it to index things, it's giving us, telling us things are indexable, and it's found a certain number of crystals. While that's running, let's swap to the other tab again and have a look inside that stream. So let's less tutorial.stream. The stream is just text, so you don't need to be afraid of opening it with a text editor. The one caveat, it can be a really, really big text file. So some text editors don't handle very large files too well, so you need to be a little bit careful. But the standard Unix less viewing tool will work just fine. So let's see what's in here. It starts with a record of the version number of CrystFEL that generated this stream. So you have a record of what version you used. There's also the command line that you used to create that, so that's recorded as well. And it's followed by the geometry file. So this is the geometry file you gave, just included verbatim. And the idea is just just that you have as complete as possible a record of what you did, so you can reproduce it. So scroll down, you need the geometry there. Okay. Now the main content of the file, of the information, is in these things called chunks. So you see the chunk boundaries here, begin chunk and end chunk. And between those are is all the information about this one image. So there's the file name, the image that got processed. Serial number is just the number in which it was given into the program, so that can be useful under certain circumstances. There's stuff like the photon energy is there. There's the detector position information. There's the peaks that were found at the peak search stage. If I scroll down and find one that was indexed, so let's see, here's one. So again, we have the chunk boundary, we have file name, we have the photon energy, camera length positions, all that stuff. Peak positions, notice there's more peaks this time, which is probably why this could be indexed. It's a much stronger diffraction pattern. And that's followed by crystals. So we have begin crystal, marking the beginning of the crystal. It's followed by the cell parameters for that crystal, unit cell parameters. The reciprocal lattice basis vectors. It thinks that it's monoclinic C-centered with a unique axis B. So we'll see if that's right later on. There are the reflections themselves, HKL, I, sigma I, and so on. Position of the peak as well. And particularly interesting are these detector shifts. So that has the shift of the detector in the X and Y that CrystFEL thought was needed for this crystal to get the peaks to line up with reality as accurately as possible. So this can be used to detect and offset. So we'll come back to more of that later. So let's go back to the tab. So it's going to take quite a long time to process the, how many were there? 5,775 diffraction patterns here. So here's one I made earlier. Tutorial raw stream, it's called. So far, we haven't used any prior information at all. So each crystal's unit cell parameters will be different. Hopefully, the most popular unit cell will be the correct one. We didn't tell it anything about what the unit cell parameters were or what we wanted it to look for at all. So we can start finding out what's going on there by using the tool Cell Explorer. You simply run that, giving it the stream file name. Wait for it to load up. This is a graphical tool. So what you're seeing here is a histogram for each of A, B, C, alpha, beta, and gamma. Histogram of the cell parameters. So these graphs, you can click and drag to move them. Using the mouse scroll wheel, you can zoom in and you can zoom out. You can change the binning by pressing plus or minus. So let's zoom into this peak, make it look really smooth. Okay. The colors of the bars indicate the centering. So this sort of purpley color, as shown on the color scale up here at the top, the color key at the top right represents C centering, and the black ones represent primitive P cell. Just in passing, if you have difficulty distinguishing the colors, you can just click them and they'll switch to black, so you can sort of highlight what they are. Now by pressing Shift and dragging, so let's zoom out here, notice there are two peaks. Well, there's a minor one here as well, but there are two main peaks. So by pressing Shift, holding down Shift and clicking and dragging, I can select peak. And what it will do now is to show in the other graphs only the unit cells that fitted that range, in this case of B parameters. So I've selected this range of B parameters, and I've said, so a lot of these extra peaks have gone away, and you can see there's a clear most popular unit cell. So let's see what that is. It looks like it's sort of a bit over 60 angstroms, 120 something, 170-ish there, yeah, a bit under 170, and then 90 degrees, and C center. So it looks like an orthorhombic C cell. To deselect, just shift and then just click instead of tracking. Note also this other one. So let's select this peak here. So now again it's sort of clear. This looks like a monoclinic primitive cell. You get both the obtuse and the acute angle representations here. So these are equivalent. But also, so probably what's happening here is this is when the indexing algorithm just didn't quite realize that the unit cell was actually orthorhombic C-centered and just gave you the monoclinic primitive one. It should be absolutely equivalent. I admit I haven't checked whether that cell actually agrees with the orthorhombic one if you apply a suitable transformation. It could also be that it's a contaminant. So this can also happen, that you get some contamination in the liquid, the crystal suspension that you inject into the beam. And then you'll see it in here, you'll see two peaks, and you'll be able to diagnose what's going on there. So let's go back to those nice orthorhombic peaks. Let's zoom in here, set the binning, plus key. I'm going to select all of the peaks. So let's get that. 90. Now from the menu here, tools fit cell will cause it to do just a simple Gaussian fit of those peaks. So this allows us to quantify the peak, the unit cell parameters. So they have 61.9, yeah, plus minus, and so on. The plus or minuses are the standard deviations of those distributions. So there we have the parameters for this sample, or what we think are most likely to be the cell parameters for these crystals. So we want to pass this information to the indexing stages, and the way that we do that is to create a unit cell file. So I've already done this. Created that here already, this file 5h2b.cell. So this just contains that information that we found. So there's a header, it says CrystFEL unit cell file version 1.0, the lattice type orthorhombic centering C, and then the ABC, alpha, beta, gamma. You could also in this file just include the lattice type information. So just say this lattice type is orthorhombic centering a C, and not include these 6 lines at the bottom here with the actual cell parameters. Now that can be a really good way of filtering, because if you do that, it will realize that the cell is meant to be orthorhombic C, and it will exclude anything that isn't orthorhombic C. And that, it turns out, can be a really powerful filter that will get you really clear results in those cell histograms. Okay, another thing I'd like to talk about at this point is those detector shifts that, remember, we saw in the stream. Now there's a helper script to help with those as well. So I'm going to copy it. It's CrystFEL scripts detector shift. So copy that to my local folder. Again, if you want to look, this is actually a script written in Python. You can read how that works if you want to. It's easy to use. You just run detector shift and then the tutorial raw.stream. And what it will do is plot a scatter plot of those detector offset values from the stream. So for each crystal, it's tried to calculate the offset that it needs to get the best prediction of the spots. And it's a bit messy, but you can see there's a clear offset from the center. So this circle in the middle represents 0,0, which means that the detector geometry is a perfect description of reality, or at least that the center is in the right position. And you can see this cloud of points is a little bit off. So let's zoom in there. That you can see that the cloud is clearly off. And actually here it estimates the mean shifts for you. So it says minus 0.12 millimeters in the X direction and minus 0.23 in the Y direction. For this detector, that's about 1 pixel this way and about 2 pixels this way. So it's not huge, but it's also, we can get rid of that. So by simply shifting the beam center position according to that position, And you can do that also with the same detector shift script. You simply run it the same way, but you give it the geometry file as a second argument there. So if I run that, it'll open the graph again. There it goes. We've already looked at that, so we can close that down. And it says there, applying correction to this geometry file. Output file name is here. So we have a new geometry file called 5httb liu 2013-pedrefine.geom. And that's the one we're going to use for the final processing. So the final command line we have is index.jig, input files.list, output tutorial.stream, the geometry. This time it's the one with the pedrefine, so the one that we've tweaked the center of. Peaks equals HDF5 like before. Indexing equals MOSFON. And the only extra parameter I'm going to add is -p and then 5httb.cell. So that's the unit cell file that I just showed you. I'm also going to have -j to go a bit faster. So the only thing I'm doing is now giving it the extra information about the unit cell parameters. So let's run that. Again, it's going to take a while. So again, here's one I made earlier. And that goes tutorial cell.stream in this case. So we can repeat the stages that we just did. So let's try Cell Explorer on this. So we should be seeing a nice clear distribution. So that's what we see. It looks good. There's no outliers. It's a nice clear peak, and we've captured the whole peak. We haven't like cut it off at the edge or anything like that. So that looks good. It looks like we've indexed them correctly as far as that's concerned. We can run the detector shift script again. Now, because for this version we used that refined center position. See, this time it says mean shifts are 0 and 0, which is good. And the clouded peaks is bang on in the center there. And it's also like a little bit neater. So it looks like the detector geometry is behaving a bit better in this case. So that's good as well. Now there's a script, another script which I'm going to copy, which is called check near brag. Copy that to my folder. What that does is the same as check peak detection that I showed you before, except it shows you the predicted spot locations. So let's run that on the tutorial cell.stream. Again, I'm going to give it the geometry, give it the refined one. It doesn't actually matter if I were to use the unrefined geometry here. So if I were to use this version, because all that does is affects the what I see on the screen. So the peaks will appear in the correct location relative to the image data. So these circle locations will always match the underlying data, but the panels themselves, so the whole thing will be offset on the screen. But that's not a problem in this case, because all we want to do is look at how well those circles agree with where the real brag peaks are. And should mention, I could also have put that that -g option inside the check near brag script itself. Remember, you're supposed to edit these scripts to customize them to fit your needs a bit better. So here's the first image that's opened. I'm going to press F5. I'm going to tweak the color scale a little bit. Let's go a bit higher. Let's go to 10. So you have to look at these and decide whether the indexing has been successful or whether it's misindexed, or maybe there's some obvious geometry problems. So this one's looking quite good, I'd say. So you can see where there are circles, there tend to be peaks inside. So you should start looking in the middle. There is a diffraction limit. So this crystal probably diffracts maybe to, we can actually put on the resolution rings here. So maybe to 4 angstroms, yeah, not much higher than 4 angstroms. CrystFEL by default will integrate all the way out to the edge. So you can tell it not to if you want to, but the default is that it will predict and integrate to the edge. So you see those spot locations, and they seem to be reasonably well centered in spots inside the circles, so that's looking good. Let's look at the next one. So again, you should look at the first maybe 10 or as many as you like, really, as many as you can be bothered to look at to judge the accuracy. So here, if you're particularly eagle-eyed, the prediction itself looks pretty good. So the things to look at, if depends how familiar you are with judging the success of indexing, but you should be looking for, so if I turn the peaks off, which I can do here, if you see like a line, peaks here, like a regularly spaced line, and also one up here, the sort of vertical line. So if I turn the peaks back on, you can see the predictions follow those lines, so that's a good sign. If you're eagle-eyed, and if you can see on the screen, you might see that within this panel, the circles seem to be a little bit too far down. So the spots inside these are actually a little bit higher up. So that could indicate that this panel is not quite in the right position. So it could be that there's more refinement to be done on this geometry file. The refinement that we did already only offsets the center, so it changes the beam center position. So the whole detector moves together. It doesn't affect those the locations within the detector. But there is another program in CrystFEL called GeoOptimizer that can do that. So if you needed to do that, you could also use that program. Okay, again, to get out of this, we just run Control-C. So now we move on to the merging step. So let's stop this. So we have a set of diffraction patterns that are consistently indexed. They have a consistent unit cell, and we want to merge them together. That's really easy in CrystFEL. You use the tool process-HKL. -I tutorial cell.stream. We need an output. Let's call it tutorial.hkl. And you need a point group. So this is the symmetry to merge according to. So in this case, it's MMM. Run that, and it will very quickly just merge those patterns. Incidentally, if you get confused about what to use for these point groups, simply look in man CrystFEL. And if you scroll down a little bit, you'll find this list of all the possible point groups that it will accept in the exact format that it will accept them. So you can look here just for a quick reference. Let's take a look in that HKL file that we've just created. It's tutorial.hkl. It's simply a text list with HKL and I and the sigma I and numbers of measurements, just for all the data in there. Now, to evaluate figures of merit, what we normally do in serial crystallography is to split the data into two parts. So with process-HKL, I can add the option even only, and I'm going to modify the file name there to be HKL1. So what this will do is merge only the even numbered patterns, even numbered crystals rather, in the stream. And then I can do odd only and form HKL2. Now, if things are going really well, if we have ideal data processing, then these two reflection lists should be absolutely identical. And the degree to which they're not identical gives you an idea of the accuracy of the data. You can compare them using a tool called compare-HKL. So compare HKL, tutorial.hkl1, tutorial.hkl2. Again, I have to give it symmetry, and I also have to give it the unit cell. So I'm giving it the -p 5ht2b.cell. That's necessary so that it can calculate the values in resolution shells. Let's run that. Actually, there's one thing I forgot, which is tell it which figure merit I wanted. So --FOM, and I would like CC, so just a straight correlation coefficient in this case. So because I've split the data in half, this CC is what we call a CC half. And it tells me the overall CC half there is 0.93. This program also outputs a file called shells.dat, which I can just look into there. And here's the CC in shells. You can see that the data seems to die around about 4 angstroms. So there's clearly nothing going on beyond about 4 angstroms. And that agrees with what we saw when we looked at the patterns. So just to make better use of those resolution shells, I can just tell it high res equals 4. It just tells it to set the high resolutions as 4 angstroms. And then just get slightly different shells, and we can see a bit more detail where the data goes to. You can also calculate a figure numerical R split, which does the same thing. So this is an R factor for calculating. This is just an R factor that compares the 2 halves of the data. Let's go to 3 angstroms this time, 3 angstrom resolution. The overall R split is 27.3, which for this volume of data actually is I'm pretty pleased with. Looking at shells.dat, and there's a value. You can see that it clearly is rocketing up. Yeah, about the 3 angstrom zone. There's also a tool called check HKL. So this works in quite a similar way, except it only operates on one HKL file. So I'll just give it my full merged data. That's HKL. That's not HKL1. That's just .HKL. Again, I give it the symmetry and the unit cell. Run that, and I think for a little while. And then I look in the shells.dat. So this is the same idea, except instead of like R splits and the correlation coefficients, it's giving me things like the completeness and the number of measurements, the measurements per reflection, signal to noise, things like that. So that's how to get those. So in the last few minutes, if you read up on free electron laser data processing, at the moment you'll read a lot about partialities and post-refinement and new ways of merging the data that are better than just a straight average, which is what the Precise HKL is doing. So those algorithms are implemented in CrystFEL in a tool called partialator, and using this is really easy. In fact, simply run partialator-i tutorial cell.stream. Again, output.hkl, symmetry, MMM. So far it's exactly the same as we had for Precise HKL. It's just that the name has changed to partialator. I also have to give it a model to use. So how should it model the diffraction physics in an attempt to merge the data as accurately as possible? The model I'd like to use in this case is Unity. And the number of iterations I'm going to do is 3. So if you look on the CrystFEL website and in the manual pages or the tutorial, it explains in a bit more detail what it's doing here. It's much more computationally expensive because it has to scale the patterns, it has to check for outliers, it has to all kinds of stages. So if your stream is very long, you might need a high-powered computer to do this. Again, you can add -j and then a number greater than 1 to make it go a bit faster. But it's running pretty well on this virtual machine here. So it's doing 3 iterations of trying to scale the data together. The model equals unity means actually that it doesn't apply partialities at all. If you wanted to apply partialities, you would use model equals either SC sphere or SC Gaussian. Those are in the manual page for partialator, of course, if you want to know more about those. Partialator writes those HKL1 and HKL2 files itself, so you don't need to do that even only and odd only stuff. So again, I can just repeat my compare HKL command just like before. I look in the shells.dat, and you can see that indeed the overall R split has decreased. So it's improved from 27% before to 21%, and the values in the shells have also improved a bit. And this is where you're likely to see strong progress in the near future in CrystFEL. So that's what I wanted to show today. A little bit over time, but for the time being, I'd like to thank you for your attention.
Thank you, Thomas. If anyone has any questions, feel free to put them in the chat window, and I will relay them. And questions? So for the data processing for the, is the bandpass of the free electron laser is such that all reflections that you're collecting are are partial, right?
Yeah, that's at least what is normally assumed. Yes.
So you assume monochromatic beam and then okay.
Yeah. Yes. So CrystFEL actually has if you saw when they flashed the streams in front. Don't know if you can still see the stream. Still see my screen. Right?
Yep.
Yeah. So there's divergence and bandwidth are in there.
Okay.
Yeah, and the post-refinement is supposed to actually refine those. But what I found is actually it works pretty well just by setting the bandwidth and the divergence to very small values, and that tends to give you good prediction. The other terms are dealt with by this profile radius. So let's find an index pattern. Yeah, so this profile radius here, that's the size that a reflection has to be in reciprocal space before it touches the, so it's the maximum distance away from the Bragg condition that the eval sphere can be while still causing diffraction.
So we have a question. How many iterations in partialator are meaningful? Where would you sort of judge convergence there?
So I normally use 3. So what I normally recommend is starting with model equals unity, iterations equals 0, in fact. If you do that, the result should be pretty much identical to a process HKL. Then go to model equals unity, iterations equals 1. That should give you an improvement already. It should give you most of the improvement. If that works, go to 3. So with some data sets, still there's some instability. So sometimes you can see lots of patterns getting rejected and so on when you use high numbers of iterations. So that's actually the thing. That's most of what we want to smooth out before you release this new version. If that works well, then try SE sphere iterations 1 and then SE sphere iterations 3. But the procedure is said to be highly convergent. So the general idea of post-refinement partialities, of course, is nothing new. It's been around since long before I was even born. And already in those papers, they commented that the procedure is highly convergent and you don't need more, certainly no more than 3 iterations.
So we had another question and I had a question. So someone asked if there's a tutorial for the geo optimizer, and I was wondering if there is a, presumably these are related amongst, a data collection run at a specific site that the geometry might be similar. Are those, is that a sort of shared resource, or does everyone refine that and optimize it independently?
Yeah, so the geoptimizer, there is, we have a full tutorial on going from nothing to refined geometry that's on its way, but it's not up yet. Shared geometry files, so at least for LCLS, they've now created a page on the Slack Confluence. So there's no chance that I'll be able to find it on the screen now, but if you search the Slack Confluence, you'll find that. And the idea is that after every experiment, people publish their refined geometry file so that everything is shared. And eventually, the hope is that LCLS themselves will provide those geometries themselves. The thing that normally causes the problems, so the locations. So let's get a file up here so we can see. Now, as you can see, the detector has 4 quadrants, and within each quadrant, there's then this 4x4 array of panels. The positions of the panels within the quadrants tend to stay more or less the same, but the positions of the quadrants can change quite a lot because there's actually this hole in the middle can be opened or closed, and that's done by sliding all of these panels in sort of upwards and vertically or diagonal directions. So the size of that hole will vary, and therefore the positions of the quadrants themselves will vary. The other thing that will vary is the central beam position. So that because the beam is not parallel to the rail direction of the detector, so as you move the detector, the beam center position will also change. So that's something that prediction refinement step that you saw should easily take care of. So that answers the question.
Yeah.
Yeah.
All right, great. Well, with that, we'll wrap this up. Thank you very much, Thomas, and
Thanks a lot.
talk to you offline.
Yeah, thanks a lot.